Welcome back to the deep dive. Today, we are going to talk about the invisible layer.
Hmm.
It is the stuff that makes the modern world work, but you usually only ever notice it when it breaks.
That's so true.
And I know, when I say the word databases, your first instinct might be to reach for the skip button.
Please don't.
You might be thinking, okay, filing cabinets and spreadsheets sounds a bit dry, but stick with me here.
Please do, because this is actually fascinating stuff.
It really is.
Hmm.
Because if you have ever streamed a movie on Disney Plus without it buffering, or if you've ever hailed a ride with Uber and watched that little car move across your screen.
In real time.
In real time, exactly. Or even if you've just checked your bank balance on your phone, you are interacting with the technology we're talking about today.
Yeah.
It's not magic, it's databases.
Exactly. It is so easy to overlook, but databases are really the unsung heroes of the digital experience. And what is most interesting about the stack of notes we have today, which comes from the AWS Practitioner materials, is that it reveals this massive shift. We aren't just talking about one big digital bucket where you dump all your information anymore.
Right, and that is the mission for this deep dive. We aren't just going to list a bunch of tools.
No.
We want to figure out why different problems require completely different engines. We are navigating that shift from the old school, rigid structures of the past to this high-speed, flexible, interconnected world of cloud computing.
Precisely. The days of one-size-fits-all are over.
Oh.
And the source material, it covers a huge spectrum. We've got relational databases, which are your classic standard.
Okay.
We have NoSQL, which kind of breaks all the rules. We've got memory-based systems for insane speed, and graph databases for complex connections. And, of course, the tools to actually move all that data around.
So let's unpack this. We have to start with the foundation, right? The classic model.
Right.
The notes call these relational databases. Now, for the non-technical listener, how should we visualize this?
The foundation is a great way to put it. When you think of a relational database, think of order. Think structure. Imagine a very, very strict library, or better yet, a spreadsheet on steroids. We are talking about data living in columns and rows. Everything has a specific place.
Right.
If you try to put a photo in a column meant for a date, the database is it's gonna yell at you.
It demands order. I like that. But in the notes, there is this acronym that keeps popping up. ACID. A-C-I-D. It sounds a bit intense for a database term. It sounds like something from a chemistry lab. What is going on there?
It is intense, but in a good way. ACID is essentially the gold standard for reliability in a relational database. It stands for atomicity, consistency, isolation, and durability. If you are dealing with critical data, you want ACID compliance.
Okay, let's break those down because I think understanding this explains why banks use this tech.
Yeah.
Let's start with atomicity. That sounds like nuclear physics.
It's actually about the integrity of a transaction. Atomicity means a transaction is treated as a single unit. It either completes fully or it doesn't happen at all.
No middle ground.
No middle ground. The classic example is a bank transfer.
All right, so say I am transferring $500 to you.
Okay, so that involves two distinct steps in the database. Step 1, deduct $500 from your account. Step 2, add $500 to my account.
Simple enough.
Now, imagine the power goes out or the system crashes exactly halfway through.
Oh, no.
The money has left your account, but it hasn't arrived in mine.
That is a nightmare scenario. I am broke and you weren't paid.
Exactly. Atomicity guarantees that never happens. If step 2 fails, the database automatically rolls back step 1. It's like it never happened.
So no half measures.
None. Then you have consistency. This just ensures the database moves from one valid state to the next. It basically means the database follows its own rules.
Okay.
It won't allow data that breaks the laws of the table structure.
Okay. And what about isolation? That sounds a bit lonely.
Isolation is actually about crowds. It means that if multiple transactions are happening at once, they don't interfere with each other.
Ah, I see.
Imagine you and I are both trying to buy the very last concert ticket at the exact same millisecond. Isolation ensures the database processes those requests sequentially or manages them so we don't both get a confirmed email for the same seat.
And finally, durability.
Durability simply means that once a change is made, it's permanently recorded. Even if the server pitches fire 5 seconds after you hit save, that data is written to non-volatile storage. It's written in stone.
I see why this matters. The examples in the notes are things like financial services, banks, crypto exchanges.
Right. Think about it. If you are moving money, you need that atomicity. You need to know for a fact that the money left your account A and D arrived in the other one.
Yeah.
You can't have mostly accurate bank accounts.
That would definitely be a very bad day for everyone involved.
Exactly. That's why relational databases like Amazon RDS are still the go-to for things like e-commerce, enterprise business analytics, content management systems. When accuracy and rigid structure are paramount, you want that ACD compliance.
But, and here is where it gets really interesting, we don't always need that level of rigidity, do we? Sometimes the rules just slow us down. The notes talk about a pivot to something called NoSQL.
That's the big shift. NoSQL stands for non-relational. If relational databases are about rows and columns and strict rules, NoSQL is all about flexibility.
Okay.
It's designed for diverse data models where you might not know exactly what the data is going to look like beforehand.
The notes describe it as schemaless. That sounds a little rebellious, like it's refusing to follow the rules of the library.
It is a bit rebellious. Instead of forcing data into a preset structure, the database adapts to the data. In a relational database, if you wanted to suddenly start tracking a customer's favorite color, you might have to redesign the whole table.
Which is a huge pain.
A huge pain. In NoSQL, you just add it. One customer can have a name and email. The next can have a name, email, favorite color, and shoe size. The database doesn't care.
So it's less like a filing cabinet and more like a, I don't know, really organized laundry basket.
A very smart laundry basket, maybe. But the real superpower here isn't just the flexibility, it's the ability to scale horizontally.
Scale horizontally. Okay, explain that to me. I know scaling just means getting bigger, but what's the difference?
Well, think of it like moving houses. With
Yeah.
a relational database, if you have too much stuff, you have to buy a bigger truck. That's vertical scaling.
Right.
You upgrade the server, more CPU, more RAM, but eventually you run out of bigger trucks. You can't build a truck the size of a city.
Right, there's a limit.
With NoSQL, you don't buy a bigger truck, you just buy more trucks. You add a second truck, a third, a 50th. That is horizontal scaling. You spread the workload across many servers.
And theoretically, there's no limit.
Exactly. No limit to how many trucks you can have.
And this is vital for massive workloads. I love the example the source material gives here. Disney plus Kai.
Disney Plus is a perfect example of why you'd choose NoSQL, specifically something like Amazon DynamoDB. Think about the volume of data there. You aren't just processing a few bank transfers. You have millions of users streaming, pausing, rewinding, creating profiles, adding to watch lists.
And they're doing it all at the exact same time.
Exactly. A relational database trying to maintain strict ACID compliance for every single pause button press globally would just, it would show.
How much overhead?
Way too much overhead. Disney Plus needs real-time data management that can handle that massive traffic without stuttering.
So while the bank is using a relational database to make sure my mortgage payment is exact to the penny, Disney Plus is using NoSQL to make sure The Mandalorian starts playing the second I hit the button.
That's a great way to visualize it. It's about prioritizing speed and scale over those strict structural rules. The notes also mention use cases like session management, IoT applications,
Internet of Things.
the Internet of Things, right, and other high-traffic web apps. If you have millions of smart light bulbs sending data, you need a bucket that can catch all that information fast. That's NoSQL.
Speaking of fast, let's talk about pure speed. The notes have a section on memory-based databases, and the stats here are wild. We're talking microsecond reads.
Not milliseconds.
Not milliseconds, microseconds.
This is the sports car category of the database world. The fundamental difference here comes down to physics.
Okay.
In a traditional database, even the fast ones we just talked about, data is usually stored on a disk, like a hard drive or an SSD. To read it, the computer has to go to the disk, find it, and pull it up.
It's a commute.
It is a commute. In a memory-based database, the data is stored in RAM, random access memory.
So it's right there.
It's right there next to the CPU. There is no commute. It's the difference between walking to the library to look up a fact versus already having it memorized in your head.
And because it's in RAM, that's how you get microsecond reads and single-digit millisecond writes. It is just incredibly fast.
Exactly.
The source highlights a specific service here, Amazon MemoryDB.
Yes. MemoryDB is fascinating because it tries to give you the best of both worlds.
How so?
Usually the problem with RAM is that if you turn the power off, the data disappears. It's volatile.
Right.
But MemoryDB is an in-memory database that is also durable. The notes say it has 99.99% availability.
And it mentions it's compatible with Valkey and Redis OSS.
That's huge for developers.
Yeah.
Redis is a very, very popular tool for building fast apps. So if developers are already using Redis APIs, they can plug right into MemoryDB without having to rewrite their code.
That makes adoption way easier.
Oh, yeah. Plus, it has a multi-AZ transaction log, which allows for a fast failover and recovery. So even though it's in memory, it's built to not lose your data.
Then we have Redis Elasticache. The notes call this a high-speed data store for internet-scale apps.
Internet scale is the key phrase there. We're
Wow.
talking about applications that have millions of concurrent users.
The example given is Uber.
Right, Uber. Think about the user experience there. You open the app and you see those little cards crawling around the map. That is real-time location data. It changes every second. You cannot write that to a standard hard drive fast enough to make it look smooth. You need that data in memory.
So Elasticache is acting like a buffer.
Or a cache.
Often, yes.
The notes mention it's versatile, used as a database, a cache, a message broker, and a queue. A cache is like a cheat sheet.
Okay.
Instead of asking the main database for the same information over and over, like who is this user, you store the answer in Elasticache so you can grab it instantly. It takes the pressure off the rest of the system.
So we've got the reliable bank vault, that's relational.
Yep.
The flexible streaming service, NoSQL.
Mm-hmm.
And the high-speed race car, which is memory-based. But what if the data isn't just about lists or files? What if it's about connection?
Then we enter the world of graph databases. The source material introduces us to Amazon Neptune.
Neptune. I love the name. It sounds mysterious.
It is deep. Graph databases are designed specifically to map relationships. The notes mention storing billions of relationships with millisecond latency.
So in a normal database, you might have a list of customers and a list of products. But in a graph database,
In a graph database, the connection between the customer and the product is just as important as the data itself. It's not just John bought a toaster, it's mapping how John relates to the toaster, how that relates to his other purchases, how he relates to other users who bought toasters, and so on.
it's the relationship itself.
It treats the relationship as a first-class citizen.
This connects to the technical detail in the notes about query languages. It supports things like Apache Tinkerpop Gremlin and Spark View.
Those are specialized languages for navigating these complex webs. And the use cases here really show why that matters. It's not just for social networks.
No, the use cases are all over the place. We've got recommendation engines, which makes sense, like people who bought this also bought that.
That's a classic graph problem, traversing the web of who liked what to find patterns.
But then it lists fraud detection. How does a graph help catch a crook?
Well, fraud is rarely a solo act. It's often a ring of people.
Right.
Maybe 5 different accounts are all using the same credit card, or logging in from the same IP address, or shipping to the same physical address. In a standard spreadsheet, those connections are buried in different rows. But in a graph database, those connections light up. You can instantly see that user A and user B are connected by a shared credit card, and that looks suspicious.
That is fascinating. It connects the dots that humans might miss. And then the one that really stood out to me, drug discovery.
Yeah.
Modeling molecular interactions.
That is mind-blowing, isn't it? It shows we're not just talking about selling widgets anymore. If you think about it, a molecule is just a complex set of relationships between atoms.
I never thought of it that way.
Amazon Neptune can model those interactions to help scientists discover new pharmaceutical compounds.
That is wild. We've gone from banking to finding cures for diseases, all using the same underlying cloud concepts.
And network security, too. Identifying vulnerabilities by seeing how different parts of a network connect. It's all about seeing the web, not just the individual points.
Now, we can't talk about AWS databases without talking about the flagship. The notes have a whole section dedicated to Amazon Aurora.
Aurora is a beast. It's designed to be a high-performance option that sits within the relational world, but supercharges it.
The stats here are pretty bold. It claims 5x the performance of normal MySQL and 3x the performance of PostgreSQL.
And that's significant because MySQL and PostgreSQL are the open source standards. For a long time, companies had to choose. Do I use the cheap open source stuff that is hard to scale, or do I pay millions for a commercial database like Oracle?
Right.
Aurora changed the game by offering commercial grade speed at an open source price point.
It also talks about resilience. It says it replicates data across multiple availability zones and autoscales.
That auto-scaling is key. But what's fascinating here is that the notes break down 2 specific serverless options for Aurora, V1 and V2.
Yeah, let's look at that. V1 is described as on-demand auto-scaling for unpredictable usage.
Right. So imagine you have a blog that is usually quiet, maybe nobody visits it at night. With V1, the database can spin down to 0 when nobody is using it.
So you stop paying.
You stop paying. Then, if you go viral, it spins up. It's great for intermittent workloads.
But then V2 is described as giving fine-grained instance scaling for very demanding applications.
The fine-grained part is the secret sauce. In the old days, if you needed more power, you usually had to double your capacity. You went from 2 CPUs to 4, then 4 to 8. It was like buying a whole new gallon of milk just because you needed a teaspoon.
That sounds expensive.
It was. V2 scales in tiny increments. It's much more efficient. It's like having a dimmer switch on your lights instead of just an on-off switch.
I like that analogy.
It gives the application exactly the power it needs, millisecond by millisecond.
And the notes also mention templates for dev test versus production.
Which is just a smart workflow feature. You don't need your testing environment to be as powerful or as expensive as your live production environment.
Yeah.
Aurora lets you easily distinguish between the two, saving money on the development side.
Okay, so we have all these amazing tools in the cloud. We have the Vault, the Bucket, the Race Car, and the Connector. But here's the problem. A lot of companies still have their data sitting on a server in their basement.
Or on-premise, as the pros say.
On-premise, right. How do they get it to AWS?
That's moving day. And for that, the notes point us to AWS DMS, the database migration service.
Is it just a copy and paste job?
It's a bit more sophisticated than that. Usually, migrating a database is stressful. You have to tell your customers, sorry, the system will be down this weekend for maintenance.
The dreaded maintenance window.
Exactly. DMS helps avoid that. It's designed to migrate relational databases, data warehouses, NoSQL. But the critical feature mentioned in the notes is that it replicates ongoing changes.
So you don't have to shut down your business for a week while you move.
Exactly. It's continuous. You start the copy, and DMS keeps listening. As data is modified or created or deleted on your old system, DMS replicates those changes to the new AWS system in real time.
Wow.
So when you are finally ready to flip the switch, the two systems are already in sync.
That minimizes downtime significantly. The notes also mention replication, generally.
Yeah.
Copying to a replica for fault tolerance.
Right. You can replicate to S3 storage or use Amazon Elastic File System replication to copy entire file systems to a new region. It's all about having a backup plan.
If one region goes down,
You have a copy ready to go in another.
But what if the language of your database is different? What if you want to move from an old, expensive commercial database on-premise to that fancy Amazon Aurora we just talked about?
Right?
They don't speak the same language.
That's where the other tool comes in, AWS SCT, or the Schema Conversion Tool.
The translator.
Essentially, yes. It inverts the schema, the blueprint of the database. The notes say you can use the fully managed version or even download the tool to your local drive. It automates the database discovery and helps convert the code so it works in the new environment.
So DMS moves the furniture, and SCT translates the instructions on how to assemble it.
You got it. It removes the biggest barrier to entry.
Wow. Okay, let's take a breath. We have covered a massive amount of ground here.
We really have.
Just to recap, we started with the rigid safety of relational databases and AC compliance, keeping our bank accounts safe. Then we broke the mold with NoSQL for things like Disney Plus Bean, where flexibility and horizontal scaling are king.
Then we sped things up with memory-based databases like MemoryDB and Elasticache, handling the internet scale speed of Uber and social media.
And we looked at the complex web of connections in Amazon Neptune, helping with everything from fraud detection to drug discovery.
Yeah.
Finally, we saw how Aurora supercharges the standard models and how DMS and SCT help us move everything into this ecosystem.
It's a comprehensive toolkit. And I think the biggest takeaway for the listener is that modern cloud architecture isn't about finding the one best database. There is no single best.
Right.
It's about polyglot persistence.
Polyglot persistence.
It's a fancy term that just means using many languages, or in this case, many databases. You pick consistency for banking, you pick speed for streaming, and you pick relationships for analysis.
You use the right tool for the job?
You build your application by assembling these different pieces together.
It's not one size fits all anymore.
Not at all. And if we connect this to the bigger picture, it raises an important question.
What's that?
Well, we are seeing databases that can model molecular interactions in milliseconds with Neptune. We have Aurora Serverless V2 that can auto-scale its own infrastructure without a human lifting a finger. These tools are becoming incredibly intelligent and autonomous.
Right.
So here is a provocative thought to leave you with. We used to design our applications first and then build a database to support them. The app was the master and the database was the servant. Okay.
But with tools this powerful, are we approaching a point where the database structure dictates the application design?
That is interesting.
If the database can find a cure for a disease by mapping molecular graphs, is the innovation coming from the code we write, or is it coming from the way we store the data? Are we building the car, or is the engine building the car?
That is definitely something to mull over. It seems the data layer is becoming the brain of the operation.
Exactly.
Well, on that note, we're going to wrap things up. Thank you so much for joining us on this deep dive into AWS database services. We hope you learned something new, and we'll catch you on the next one.
Thanks for listening. Keep learning.